Okay, last time we talked about the theorem on the trace and determinant of eigenvalues. And this time, let's talk about the theorem of if A is a triangular matrix. We all know what triangular matrix is. And the eigenvalue of A repeated with multiplicity are the diagonal entries for triangular matrices. So for example, if A is 2405, then it has two eigenvalues, and that is lambda 1 equals 2 and lambda 2 equals 5. So if we have a normal matrix, it's not diagonal or triangular, how can we find a similar matrix? As we introduced last time, similar matrices have same eigenvalues. Okay, to find that is called the eigendecomposition. So any matrix A, if it's diagonalizable, then we say it can be eigendecomposed to a matrix of eigenvectors, and the middle lambda matrix is a matrix of all the eigenvalues on the diagonal entry, and Q inverse is the inverse of the eigenvector matrix. So such matrix can be found by, we know that to find lambda and v, to find eigenvalues and eigenvectors, we have this equation. Matrix multiplied by v equals a lambda multiplied by v. So then we can write, so if we want to do a times vi, then we can also do like v2, v3, like every eigenvectors. We can put it in the matrix. And on the right side, so the first column I have a times vi. So my first column would be equivalent to lambda I times vi on the right. So same thing for a times v2 is the same as lambda 2 times v2 because those will be equal. And we can further write the right side to be a matrix of vectors multiplied by lambda values put in the diagonal matrix. So then when we multiply these two matrices, it'll be like all of the first row multiplied by lambda I, but what we're doing is actually just the first entry of v1 multiplied by lambda 1. And then similarly for the second row, what we're doing is the second value in v1 multiplied by lambda I. So then what we have here is actually the matrix Q, exactly the same as this, multiplied by a matrix lambda, capital lambda, which is composed by eigenvalues on the diagonal entry. All right, so then let's multiply Q inverse on both sides on the right. We would get A equals Q times lambda times Q inverse, and that's called eigendecomposition. And a lambda and matrix A can only be written like this if and only if the algebraic multiplicity of lambda or lambda I is equal to the geometric multiplicity. For the same lambda I. Okay, what matrices can be diagonalized? Let's we're in chapter 4.2, section 2 on diagonalization. So basically, we all know that for a diagonal matrix, the determinant of A equals just the diagonal multiplied together, because a diagonal matrix is just a special triangular matrix. And the eigenvalues lambda are also a1 through an. And there are some properties such as if we have two diagonal matrix, multiply A multiplied by B equals B multiplied by A. because for each entry is the multiplication is commutative, because that's in the space of either C or R. All right, and we also have, if we raise the matrix A to the nth power, it's the same thing. It's like A multiplied by A multiplied by A. So all the operation is done on the diagonal. Okay, we have an example. So if we have a matrix A that's 3, 1, 1, we know that we have two lambdas. We have two eigenvalues. The first one is 3 with a algebraic multiplicity equals 1. The second one is 1. So lambda 2 equals 1, but it appears twice. So that's the geometric multiplicity equals 2. Okay, and when lambda 2 equals 1, we can compute the eigenvectors so that we can know the geometric multiplicity. So we find the matrix of A minus lambda I, and we compute the vector to be 0, 1, 0 and 0, 0, 1. That means we have two eigenvectors. So our geometric multiplicity of lambda 2 is 2. Same thing for lambda 1. We have we compute A minus lambda 1. That's the matrix only has two entries right here. So then our eigenvector is 1, 0, 0, or the span of 1, 0, 0. So our geometric multiplicity is 1. And in this case, the standard basis vectors are the eigenvectors. So actually, if you're dealing with the diagonal matrices, our eigenvectors would be the standard basis vectors. Okay, so a definition. We will introduce a linear transformation that maps from V to W to be diagonalizable if there exists an ordered basis B of V such that TBB is diagonal. And we all know that linear transformations are associated with the matrix A. And we say this matrix A is diagonalizable if TV equals AV is diagonalizable. Okay, so there's a new notation, this TBB. What does that mean? So let's look at the definition. So for a vector space V with an ordered basis, so this B from B1 through Bn is ordered. And the coordinate of V, what we said before, is the coefficients on B1 through Bn. And each coefficient forms all coefficients forms a vector, and that's called the coordinate of V. So we introduced it from at the beginning of the class, like the first lesson or something. Or when we introduced the linear combination. Okay. So we basically say V is a linear combination of the bases. We all know that. And if they are ordered, alpha 1 through alpha n are a coordinate of V on base B. Okay, so for example, if we have a set of standard bases in R2, and we know V equals 1, 3, that means V equals 1 times the first standard basis, E1, which is 1, 0, plus 3 times E2, that's 0, 1. And we can write it in any basis. So if we're given a basis, another basis in R2, that's B. So these two vectors are linearly independent and spanning, so it's a basis. And we can compute what our coordinate is in with this set of bases. So we just solve the equation. We have v equals alpha 1 times times v1 and alpha 2 times v2. So then 1 equals alpha 1 times 1, alpha 2 plus alpha 2 times negative 1, and 3 equals alpha 1 times 1, alpha 2 times 1. So we end up with alpha 1 equals 2 and alpha 2 equals 1. Okay, so then that means our same vector v with base b, the coordinates would be 2, 1 instead of 1, 3. All right, that's about vectors. Now let's introduce the notation of a transformation. So if we have t is from v to w, and we let it to be linear, and we let a basis a to be a1 through an, an ordered basis, and b equals b1 through bn, an ordered basis of w. So then our matrix T with respect to bases A and B is called TBA. So that's basically we do the transformation of our basis A, because the transformation is from V to W. We do a transformation of all the bases to our new vector space W, and then we need to translate them with basis B. So we do the transformation of A and then represent it with basis B. So similarly for others, we do the transformation and then represent it in B. All right, let's do an example. It's quite abstract. So if we have a matrix A and our transformation is from R2 to R2, so we have a TV equals AV. Okay, this matrix, we already calculated the lambda, the eigenvalues last time. That was right here. So we know that our lambda equals 2 and lambda equals 3. All right, so then let's look at where it is. All right, let's look at when lambda 1 equals 2. Oops. We already know that the span is the eigenvector is the span of 2, 1. And when lambda equals 3, the eigenspace is the span of 1, 1. Okay, and we will use them as the basis. So we have a basis B in R2 with these two as bases. Okay, now for this transformation TBB, it will look like T transform the basis with our new basis B. So we transform the first vector 2, 1. So we do a matrix A multiplied by 2, 1. That gives us 4, 2. Same thing, we transform this 1, 1. This matrix multiplied by 1, 1 gives us 3, 3. Okay, but now we need to express them in the basis B with this set of bases. Okay, and now we just do a vector representation. So to represent V2, to represent 4, 2 with these two vectors, we know that it will be 2 times the first vector plus 0 times the second vector. So it'll be 2, 0 in the first column. So similarly for this one, it will be 0 multiplied by the first vector and 3 multiplied by the second vector, so it'd be 3 1 0 3, I mean. Okay, and now what we have here would be a diagonal matrix, and these two are actually our eigenvalues, as you can see. So our Q is just the ordered basis 2 1 and 1 1, and our lambda is this diagonal matrix 2 0 0 3. Okay, so then we can actually check if Q times lambda times Q inverse gives us this A. So we know Q is 2 1 1 1 multiplied by the lambda 2 0 0 3, and Q inverse we know is 1 over the determinant multiplied by dA negative B negative C. Okay, so after the calculation, we get 1 2 negative 1 4 in the end, and that's exactly our A. All right, so then our next theorem. So we say the following 3 sentences or statements are equivalent. That means whenever we know one of them, we know the other 2. The first one is A is diagonalizable. Second one is there exists a collection of eigenvectors for A, and that eigenvectors b1 through bn forms a basis, capital B, for the space Rn. And the third statement, or Cn. And the third statement is there exists an invertible matrix Q with QAQ equals D, where D is a diagonal matrix. Okay, so let's say an example. If we have a matrix A and we find the eigenvectors, we set the determinant equals 0, and after some computation, we simplify the whole determinant to this characteristic polynomial. And then we set it equal to 0 to solve for the eigenvalues. So by observation, we know one of the eigenvalues is 1, and then we do a polynomial division to find the other factors to be negative lambda plus 1 times lambda subtract 6. So we have 3 eigenvalues, but lambda 1 equals 1 with a algebraic multiplicity to be 2. And lambda 2 equals 6 has a multiplicity of 1. Okay. And now we calculate the kernel. We find the kernel and we calculated the eigenvectors. So when lambda 1 equals 1, we have 2 eigenvectors. And when lambda 2 equals 6, we have just 1 eigenvector. Okay, and now we can actually write the lambda and our Q. So our lambda, when lambda 1 equals 1, we have 2 rows. And then that's the corresponding eigenvectors right here. So same thing, when lambda 2 equals 6, we have our eigenvector to be 0, negative 1, 1, negative 2. And that corresponds to our third eigenvalue, 6. Okay. So then we can calculate the determinant of Q. And if the determinant of Q is not 0, then it's an invertible matrix. So it means that we can find a Q inverse. And it also means that the eigenvectors, because all the columns are the eigenvectors, And it means that all the columns form a basis, so the eigenvectors form a basis. Of our R3, R cubed. Okay. So this one, we know that lambda 1 has a multiplicity of 2. It has a geometric multiplicity of 2 as well. And lambda 2 equals 6 has an algebraic multiplicity to be 1, and it has a geometric multiplicity to also be 1. So that means it is diagonalizable, and apparently it forms a basis since we verified here. And it also can be written as a, we can also find a set of Q and Q inverse so that A has a similar matrix to be a diagonal matrix D. That's our lambda right here. Okay, so this matrix verified all three statements. Okay. And then we introduce the theorem. So if lambda 1 through lambda r are distinct eigenvalues, and lambda 1 through lambda, v1 through vr are corresponding eigenvectors. So that means if we have 1, 1, and 6, we only consider 1 once. So we would have like 2 distinct eigenvalues in this case. Okay. And in this case, the corresponding eigenvectors v1 through vr are linearly independent. That's the theorem. And there is a corollary saying if a n by n matrix has n distinct eigenvalues, then it is diagonalizable. So if A has n distinct eigenvalues, that means v1 through vr are linearly independent. And we know that if n by n matrix has n linearly independent vectors, then it spans the space Rn. So if it's linearly independent and spanning, it is a basis. Okay. And we know that if we can form basis, then it's diagonalizable. All right. We will prove the theorem next in our next video.